Hey 8th graders, it's Mrs. Thompson. We're going to jump into chapter 8. We're going to talk about quadratics. It's this entire chapter, and we're going to definitely get it started here with 8.1, example 1. Now, by the time that this particular section is done, I think we have 4 examples to cover. We're going to do the first example in this very first video. Our goal in this section is to identify quadratic functions, determine whether they have a maximum or a minimum, and then we're going to learn how to graph a quadratic function and give its domain and range. We're not going to do all of that in this first example. We're going to do just a little bit of that. Now, let's get to some definitions. Quadratic function. As you may recall, when we were classifying polynomials, anytime you had a polynomial where the biggest exponent is 2, we classified that as being a quadratic. So that's why this is a quadratic function. It's because the biggest exponent on our variable, our x variable, is a 2. And so if you have a squared variable, and that's your largest exponent, it's definitely quadratic. So that's the way you tell. So I circled the basic equation, the standard form of the equation, y equals ax squared plus bx plus c. A, b, and c are all whole numbers or integers, okay? And then x squared and x are your variables, okay? Looks suspiciously like a trinomial. Remember doing that in chapters 6 and 7? We learned what that word meant. We have 3 terms. We have a trinomial. And when we have a trinomial with its largest exponent is a 2, then it's quadratic. Now, the graph of a quadratic is a parabola. So it can open up, so it has that very typical cup shape, kind of a soft U, or it can open down, just like that, okay? And the parent function is right here. Notice what's missing. We don't have a bx or a c, which is fine. You don't have to for it to be a quadratic. As long as there's a squared variable and that's your largest exponent, then it's definitely quadratic. What makes this special is that it's the parent function for quadratic. Now, as you may recall, when we studied lines, when we did linear equations, you know, we talked about different forms. You know, here's slope-intercept form. We talked about that form. The parent function for a linear equation is y equals x, okay? Now, a parent function, I'll go ahead and tell you, parent functions always go through the origin. So if you are told, for whatever reason, hey, this is a parent function, whatever the graph is, and you are told or you read this is a parent function, it goes through the origin. That's the hallmark of a parent function. We know that to be true, okay? So let me just graph the parent function for you, y equals x squared. I just kind of wanted to show you what it looks like. I'm going to do a little xy table, and I'm going to plug in -2, -1, 0, 1, and 2. And we're expecting it to have that typical U shape, very soft U, nothing, no jagged edges or anything. So let's plug in for x. Let's start with the -2. -2 squared. Remember, in your calculator, that goes in parentheses, and then you square that. When you square -2, you're going to get +4. So one of our points is going to be -2, +4. Now we're going to plug in a -1. In your calculator, that goes in parentheses. Anytime you square a negative number, put it in parentheses. -1 squared is +1. 0 squared is still 0, nothing changes. 1 squared is 1. 2 squared is 4. Okay? So we have enough information to graph the parent function for a quadratic equation. All right, so let's start with -2, 4. So we're going to start here at the origin. We're going to go back to -2 on the x, and then we're going to go up to +4 on the y. And then we're going to mark it. Looks great. Okay? -1, +1. So we're going to go back to -1 on the x, and then +1 on the y. Mark it. We're going to go to 0, 0. There it is. We knew our graph would pass through the origin. It's a parent function. It's going to pass through the origin. 1, 1, and 2, 4. Okay? And then look what you've got. This is your parabola shape right here. It's a soft U, and there it goes. That's what a parent function looks like for quadratic, okay? For linear, remember, it's a straight line. It's going to go through the origin. Oop, I didn't mean to do that line, so just kind of ignore that. So y equals x. So anytime I plug in -2, y is the same thing. -1, y is the same thing. 0, 0, 1, 1, 2, 2. So it should be a straight line. -2, -2, -1, -1. Whoop, something popped up over here. Let me bump this back down. Sorry about that, guys. There we go. -1, 1, 0, 0, 1, 1, 2, 2. And see, even a linear function, parent function, still goes through the origin. Notice that, goes through the origin. So that's what I wanted to point out to you. We will talk about the parent function later in chapter 8, but I wanted to introduce that concept to you now. Parent functions, all graphs of shapes have a parent function. So whether it's a linear equation, whether it's an absolute value equation, whether it's a quadratic equation, you have a parent function for all three, and they all three go through the origin. Okay, well, let's get to our objective for today in this particular example, and that is we're going to identify quadratic functions from a table. So that's what letter A is all about. We have a table here of data that we need to evaluate, and we got to tell whether each function is a quadratic and explain ourselves a little bit. And that's my job. So I'm going to do A, B, and C with you, and then I'm going to leave the quick checks for you to do as bonus points. So I'm going to leave this as extra credit, and I'll give you a point if you can figure out these two. But let me demonstrate A, B, and C to you first, and that'll give you enough information to maybe pursue the quick checks. All right, now, a quadratic function from a table. Yes, you could get out some graph paper and graph those points and see if it has the hallmark shape of a quadratic, which is a parabola. Yeah, you could do that. Would I do that? Absolutely not. That would really, there are a lot of other ways to do this than graphing. I wouldn't waste my time doing that. So what would I do? Well, the first thing I would do is I want to make sure I have a constant change in my x's. So as you go from -4 to -2, you added 2. -2 to 0, I added 2. 0 to 2, I added 2. 2 to 4, I added 2. So I need to verify that I have a constant change in my x. Okay, so I verified it. I definitely have it. All right. Now I'm going to do the same thing with my y's. Okay. So how did I get from 8 to 2? Well, I took away 6. How did I get from 2 to 0? I took away 2. How did I get from 0 to 2? I added 2. How did I get from 2 to 8? I added 6. Okay. There's a little bit of a problem here. I don't have a constant change in my y. Well, in quadratics, I don't want a constant change in the y, because if I did, if I had a constant change in the x and a constant change in my y, then what would happen is that would actually be linear. We studied this when we studied linear equations. Constant change in x, constant change in y is linear. If you don't see that same number all the way down when you check for that constant change, then it's not linear. And we don't. We have -6, -2, +2, +6. So this is how you tell if it's quadratic. You now take these numbers and you find the difference between these two numbers. So how did I get from -6 to -2? I added 4. How did I get from -2 to +2? I added 4. How did I get from 2 to 6? I added 4. This is what you're looking for. And what we call it in algebra is a common second difference. If your table has a common second difference, it's quadratic. If your table has a common first difference, here's our first difference right here where I've underlined, then it's linear. Okay? So I'll write that kind of up here in the margin. Linear common first difference. Okay? Quadratic is common second difference. That's how you tell which one you're dealing with. Common first difference, hey, that's a linear equation. If you have a common second difference, because all the numbers in your first difference are different, then it's a quadratic. So this is definitely quadratic. And the reasoning behind it is because it has a common second difference. Okay? So that's the answer to this question, to letter A, using a table. Now when you do quick check 1, it's not written in table form, but you can write it in table form and then check it out. See if you have a constant change in your x, which you should, and then look for your common second difference in your y's. Okay? Now let's move on to letter B, y equals negative 3x plus 20. Okay? Remember I told you on the front page, a hallmark of a quadratic function is your biggest exponent is 2. As you look at this x, what's the exponent on it? A 1. So it's not quadratic. And it's actually linear. This is in slope-intercept form, so it's not quadratic. It's linear because it's in slope-intercept form, y equals mx plus b. And x is raised to the first power. So when your biggest exponent on your x is a 1, it's linear. If your biggest exponent on your x is a 2, it's quadratic. Okay, that's how you tell. That's the basic difference. Then let's look at C. Now we've got y plus 3x squared equals negative 4. What I would do is get y by itself. So I'm going to subtract 3x squared from each side. And I've got y equals negative 3x squared minus 4. And so as I'm looking at this, I'm specifically honing in on my variable, and that's my only variable, and I'm looking at the exponent. That's really what I'm interested in. Hey, there's a 2 on it. My biggest exponent is a 2. That's definitely quadratic because it's almost in the form of y equals ax squared plus bx plus c. It doesn't have that bx term, but we can put a ghost term in like 0x if we wanted to. So it would, if I did that, that's what this would look like. And you would put if you don't have a bx term, just make it 0x and you've got it. But that's definitely in the standard form for a quadratic function. Okay? So letter A, common second difference. If you're given a table of data, look for a common second difference. If you got it, then it's quadratic. Letter B and C, look at those equations. If your x has a square variable, and that's the largest exponent on it is a 2, it is quadratic all day long. If it doesn't, then it's not quadratic. Okay? So now, you guys try quick check 1, quick check 2. I want to see if you think it's quadratic, and then please write your answer. Okay? So it's quadratic or not quadratic, and if it is quadratic, why is it? What's your reasoning? All right, good luck with that, and I'll check with you tomorrow.